for our Black-Scholes mass. And this was the explanation, but the Black-Scholes mass is here. This is the Black-Scholes formula itself. And the problem is that we can take the implied vol and compute D1 and D2 and put it into the formula and get the dollar amount now. Now, what if we have the dollar amount and we want to know the volatility? You cannot invert it easily. There is no analytical solution. So you have to use a numerical solution. And the numerical solution is called generally root finding scheme. And I have the, in exercise solutions, a Newton-Raphson because it is I find to talk about it analytically quite easy. But in older days, even before the computers, what they had pre-computed values of the Black-Scholes printed like a book. So if the asset price is 4 and the other parameter, the volatility is 20, then you look at the like tables and you look for a particular section of the book and you find the option price. But that was fast enough because otherwise the computers were not catching up with this inverse root finding. The root finding though is set up simply as this. So we have the function f, and the function is the price the option price with the volatility or the option formula with volatility as the input minus the market price, which and this should be equal to 0. Let's see what the 557. So if the market price is 557, so V minus 557. Now to solve this, to find the sigma, this is called a root finding task. And what we do is we take the derivative of this function. Now, the f is really v. Now, because the derivative of the 557 number will be equal 0. So this is simple derivative, discretized, right? Volatility plus, option with volatility at k plus 1 increment, not time increment, minus vol at k, divided by the change in variable itself. So, okay, now what I do, I rearrange this one to get the function value at k plus 1. So that would be equal function value at k plus this expression. Okay, I did that. Now I need to actually get myself to the estimate or guesstimate for the sigma at k plus 1. So I keep rearranging and I have this. Now, if I have the correct solution, then this function at k plus 1, if I get my volatility correct, is equal to 0. Because this should be equal to 2. If I put correct v, if I put correct sigma to compute v, that should be equal to 0. So if the function is 0, this one will vanish. And then I have my scheme for updating the volatility. And if we look at the scheme, so we'll take volatility k, so minus f sigma k divided by the derivative of that f. Or simply speaking, essentially the f is v minus market price divided by vega. So you need some initial estimate. So the first sigma k, so sigma 0, you take some reasonable value, let's say 20% or 10%, something, and then you compute sigma 1, and then based on sigma 1, you compute sigma 2, and then until you arrive at the correct answer. using this updating scheme. So you put sigma 1 20% in here, then you compute option price minus 557 using 20, compute Vega using 20, and then compute next sigma 1. Then you put sigma 1 in the scheme and keep computing it. So if you do that, you will finally arrive at the correct answer for this option, which is which was roughly 20%. So if you start, it's all subject to the tolerance. So you have to start with, well, it will probably give you your 20% as sigma 1 and you finish. But if you start with guess at 15 and then keep computing it. So this is the Newton-Raphson scheme, and the code for the Newton-Raphson, and I have is in the document, and I have it in several languages. Well, C++ is kind of long with declaration, but even if you don't know, you can easily see what I'm doing, because this is where I am updating the function. And again, I shift, let's say, if you don't know R syntax, you still know that this is when I'm updating the volatility, and I keep doing it until I get the result, the difference of the Vk minus Vk plus 1 subject, below the tolerance. So just again, in any language that you like, and there is one in Python, so the implementation of this Newton-Raphson scheme. Again, there is no analytical solution. You have to do the root finding numerically. So we did the solutions, Newton-Raphson root finding. All discussed. Okay, Vega. Again, you have the exact values, but you cannot estimate the Vega risk unless you can look at the, for example, historical wall and see the implied wall starts to diverge pretty much with historical. Well, in this case, you would be making a profit because the implied wall, usually the implied wall diverges from historical, this is good situation. But then if you see the historical catch up very quickly, then you know that your implied wall is not going to be, pushed up to it because it simply will be too expensive. So the Vega can be small, but the change that can come is a lot. Vega is a Greek, it has a formula, it's computable. So it gives you the specific answer. So if the wall goes by 1 percentage point, you can compute the change in the option, and that would be, the option is written per 100 shares, so it usually will be quite significant. So 1 percentage point move in wall is quite significant business in cash price of the option, typically. And then, quick example, I'm not going to stop, but essentially what this example tells you that you can, if you have several options, you can add up the deltas arithmetically and the gammas arithmetically. In this case, you can actually, for example, have portfolio that delta and gamma neutral, and you can figure out the weightings, and it will tell you the weightings for this particular situation, because to have delta neutral, you equate delta times weighting into asset A plus delta asset B or option B weighting into option B. So the The Greeks, again, for the portfolio, you can add them up. And stock has delta of 1 and gamma of 0. And stock has no vega. That's done. Now, in terms of the managing risk for derivatives, the Basel part that deals with that called Fundamental Review of Trading Book. It's a document. You can find it, the section of on the Bank of International Settlements website under the FRTB. And if you open the FRTB document, there are two versions, but the recent version is which is the Basel III version. It just simply talks about delta, gamma, and vega. So the delta risk is risk if by how much option price moves. If the asset moves, the gamma is change in delta, and the vega is the change in response to the implied vol change. And the only slight difference that the Basel calls gamma a curvature risk, and vega is called the vega risk. But that's the same. So if you have a position in the option, the P&L for a future period would be delta times delta S, half gamma times delta S squared, theta times delta T, plus the vega times delta vol. It's a question, of course, which delta S, delta T, and delta vol you'll be putting into the formula. But this is the standard, the Basel III expansion for an option risk management. Okay, if I go to this one, to these charts, I better switch to my Excel. Now, this Excel file, I will open VBA for you. It's like a mini library in VBA of all sorts of functions, by the way. So it's not just a file. It's like you have it everywhere. I mean, inside you have everything that you need. So if you open Visual Basic all the time in this Excel file that is distributed with the lecture, you would see, for example, the VBA function for the option price, to compute the delta, to compute the gamma. Formula on the spreadsheets are coming. But the one interesting thing, though, that look at the function that, so the gamma, apologies, delta is the normal CDF. Normal CDF is computed using the approximation that has, well, 5 constants. So it's a function over the 5 constants. So it's exponent and then the powers in the exponent. So this is what you do, or rather this is what you have to do with Excel, because otherwise it is becoming painfully slow. Imagine if you compute option price in every cell. And every cell, if you use like a standard normal Excel norm inverse or norm CDF, it will do numerical integration for every cell. The spreadsheet can go very slow. So therefore, sometimes it makes sense to implement your own simple numerical procedure in Excel, which gives you pretty much the same result precision-wise, but will not make your spreadsheet painfully slow. Well, this was, of course, very crucial to, like in early 2000s, because Excel wouldn't be, taking it now. It's more faster, but still makes sense. Now, in terms of the Greeks, we have the formulae on the right-hand side. So this is the delta and D1. Look at the gamma. So gamma is ND1 derivative, and then D is derivative of D1, and the derivative of D1 comes down to the 1 over S, because there is log K over S in D1, if you remember. So it comes down to 1 over S, sigma, and so on. And this is vega, which is, So so you see the vega is proportional in dollar terms. And I have 2 scenarios. So one scenario is the option price at 20 vol and another at 30 vol. And 30 vol is delta plus. So you see, I increase volatility and my payoff becomes more smooth. So if I change, I believe I should change this one. If I change delta to 40, so you see, and this is the think about implications for the delta hedging. The higher volatility gives you smoother curve, so you can be fast enough moving on this curve. So if the volatility in the market is 40, it's easy to delta hedge. And look, if the volatility in the market, like we have more or less now VIX 12, apologies, I have to do the 12. No, that would be super smooth. 12. Look, if the volatility is 12%, it's actually extremely difficult to hedge because we're very sensitive here. It changes really fast. So here you have to hold 100 shares. Here you have to hold 0 shares. So you have to go from 100 to 0 over the very short price range. So it's actually difficult to do the hedging in the low vol environment. And a lot of institutions actually close the option market making desks. And even Interactive Brokers, they had like an independent subsidiary based in Switzerland, which was quoting the options, and they even closed that. So the options that you buy on exchange is most likely to be sold by some broker, some division rather than the big institution. But anyhow, the Mohan the question. Okay, the Mohan's question was about the P&L for the FRTB option value expansion. So I haven't introduced the idea of hypothetical P&L because that's new. That's Basel IV. But back to the Greeks, because we're still dealing with the Black-Scholes rather than regulation. This is the delta, and as we see that it's much easier, much smoother to hedge. So 40% volatility, the delta is a much smoother function than it is at 12%. Now, and that translates to the gamma. So this delta plus have a small amount of curvature here. So the delta plus correspond to the gamma plus, and the gamma plus is not very high. So you are not short gamma in the sense that you're not having too much gamma to respond to. And then the delta of the 12%, which is in the dark blue, have the gamma here corresponding in yellow. So 12% vol has this delta and a lot of curvature because it's rising fast, so which means we have a very peaking gamma. And then from the viewpoint of options hedger, high gamma is good if the asset price moves up well, but it's actually not good if the asset price doesn't move. Because why? By the way, why? Because the high gamma is your theta. Gamma is the same as theta. Theta is a gamma with negative sign. So you will be paying this, and the asset price should be moving up a lot for you to compensate it. All right. So this is the illustration, and in terms of the slides, this is how it's all codified. So in terms of the simple option value, so this is the call payoff. Again, so this is payoff, let's say at 30, and this would be payoff for the option at 20. Now, of course, it corresponds that at expiry you have no curvature, at expiry you have line. So this 0 at expiry. Okay, so the higher the vol, the smoother the payoff. Delta, we saw the example. So this is 30, this is 20. And again, gamma. So that means, again, this is a sigma implied, 20 used to compute gamma. And then sigma implied 30. So to give you the interesting bit, before talking about the smile, which is more or less a standard thing, we assume that the market is wrong. In this case, we're saying that the implied one is not the one that should go into the ND1. So we'll see what we can do about it. Now, this is the position of a buy side when you try to arbitrage against the the cheaply priced option. But usually, again, if you think that the implied one is correct, then, or at least not necessarily correct, if you think that the implied one carries information about forward volatility, then you have to, again, bootstrap that forward volatility and compute your delta, use that bootstrapped sigma t or sigma ts, the local wall. So the second way is what classically the sell side is doing. But they're not doing it to market make the vanilla options. They're doing it to create the model against which they will be marking the conflict exotic. So it's not for vanilla calls and puts the second way. And of course, there's lots of limitations on this trading these days, but this is at least the purpose. And by the way, if you're not aware, I think there are talks about removing proprietary limitations on the financial institutions for the proprietary trading. There are talks in the US, and if the current administration will pass the changes to the Congress, we are back in business. It'll have explosion, a lot of work, a lot of employment if the banks can do the proprietary trading again. But yeah, they at least they're preparing the law. We'll see if they can manage. Here we go. Before that, the couple of reasons and the problems with the Black-Scholes. The out-of-the-money puts give empirical proof why markets are wrong in predicting vol. Why? Because the out-of-the-money puts is usually priced cheaply in dollar terms, but because they're deeply out of the money, or you say, yeah, 50 cents or $1 doesn't look much. But if you convert that 50 cents into the implied vol, it will be very expensive. And it's actually with puts, you can open the picture and you would see you going out of the money and your implied vol increases actually. So it goes like 20, 30, 20, 24, 26, 25, and then very deeply out of the money puts are actually very expensive in implied volatility terms. Could be it's quite amazing because it's out of the money put and it costs 50% vol or 46% vol compared to the normal 20% vol in the asset that you can observe typically. And you can say, oh, is it the correct prediction? So, well, it's correct in the logic of the put because yes, if the market will be panicking, then 56% is prediction, and that out of the money put will reach the moneyness. But the expensive not because of the good prediction. They're expensive just because no one will sell it for you for 10 cents. They will sell it for you for 50 cents or for $1, simply not cheaper. Because they know that there will be buyers for out of the money puts because of the fear. And this is so the out of the money puts, if you look again at them, and particularly out of the money puts as a function of the strike, you will typically see the implied vol increasing. And then again, that's empirical proof against Black-Scholes. And with Black-Scholes, we have the Vega risk, which is uncertainty in implied vol. And there's a specific class of, when they say uncertain vol, it's a specific class of the models when you guess minimum and maximum. And then you can reformulate Black-Scholes with min-max, and you can find numerical solution, because when you do the finite difference, you can actually assume worst case. You choose the vol from minimum or maximum, depending what's your worst case, and you can price the vol price like under the worst case scenario. Whichever the vol higher or lower is worse for the price of the option. That kind of thing is also possible. But yeah, the options usually underestimate the default risk, the first 2 points, the effects of the discrete hedging I was talking earlier, that you have to smooth. If the curve is smooth, yeah, imperfect discrete hedging is not a problem. But if your delta is sharp, then discrete hedging is a problem. Now, there is a lifelong lectures, couple of lifelong lectures with some mathematics around it. So I'll write it extra. On the first 2 topics, and they introduce in transaction cost and how would Black-Scholes look with bid-ask spread. It's all developed. If you can look into it. Okay. And now there is also, if you're talking about non-standard option, then when you sell it to the other, you sell it, the other party worries about your counterparty risk. So we are talking about computing for the OTC options. We are talking about computing the credit risk adjustments, and against which you have to hold capital. So it's additional price to the option, because capital costs overnight rate. It's small, but it's non-negligent. So in that sense, there's again a lot of talk about the fair value, but there is no fair value to the quoted option. And a Black-Scholes is not a model that talks to you anything about the future, because implied vol is not a forward vol. Okay. Now the arbitrage situation. Assume we have scenario. The implied vol is actually happens to be low, and you can buy an option valued at 20% implied vol, assume, and the actual move in the asset price will realize at 35. So what would you do in this situation? What's possible to do? Well, so if the option is cheap, we are not going to get greedy. We will buy it. But so that will be our cost. So we need to find those money somewhere. So we need to make those money from a market. We are making it by replicating. So if we would be delta hedging a call, we would be holding a stock. But because we bought a call, we not hedging, we're replicating against it. So we are selling a stock. So that's the only difference. So we buy an option, and we delta replicate. So we buy at 20, and through the delta replicate, we should make up the premium from the market, but the premium should be at 30, and therefore we have the hedged profit at 30 minus 20 at 10%. We'll see how much it in cash. But yes, the cash position is inverse of the derivatives position. So the cash to buy option priced at VI at 20%, the cash is minus VI, and then since we are selling the quantity of the stock, our position on cash position from the sale is positive. Now, of course, what happens on the next step is math. I will see how it will behave on over t to delta t. So I'm interested in the increment of this position. So notice that this is the cache, right? So the cache and the leg and the option leg which is exactly the opposite, the hash position. Or in this case, replicated position. Okay. Again, the point is that by doing this, by selling assets short and actually earning on that short sale an interest, we should earn a pile of money that is equal to the option premium. The result of this strategy, so this is priced at the actual, let's say the actual over the lifetime will realize at 30. And this is at 20. So clearly the Black-Scholes price, if you can compute, one would be, given the other parameters all the same, it's the same asset. So clearly at 30 it will be positively above at 20. So the profit is guaranteed. Let me show it mathematically for you. So at time t plus dt, I have the option changing v plus dv. So if I would do the differencing, so the P&L, if I take the difference, so I need to take t plus dt and subtract what I have at t. Okay, so here I have, in terms of the difference, dvi. Here I have minus minus will give me a plus, so I will have simply minus delta A ds. And then I will have this expression minus vi plus delta A s times r dt, because it's just 1 plus r dt, so that's the differencing. Now let me add up all of this differencing. So I take this plus this plus this. Okay. Now if the option price correctly, so if sigma A is sigma I, then as we said, this sum should, so if dva minus delta computed using sigma A, so if all of that story is the same, then it's equal to 0. Now I do the following trick. I say if it's sincerely equal to 0 for the correctly option priced, I will subtract that 0 expression from the first one on the top. So I take the double dagger and subtract it from dagger. Because I'm subtracting 0, shouldn't change. But it will give me the interesting result. So again, so dvi minus dva and so on. I will get this one and I fold it because there will be some cancellation. This will be cancelled out. And I will fold it into this result, which in turn I can write as dvi minus r vi dt minus, and then dva minus r va dt. Okay, so I observe that, and then with the help of integrating factor, I know that every time I see something like dvi minus r dt, I can fold it as d discounting factor v. So if I see again something like this, I can if I pre-multiply it by the integrating factor, and in this case, you see I pre-multiplied it, and then to cancel it out, I multiplied it by the RT outside the bracket. But inside, so if I see something like dv minus rv dt, I know I can fold it into the derivative so I can multiply both parts by e to the power of RT. So in this case, it will cancel out, but you see what happens. Okay, so that's done, and then, but this is my increment over the. This is still over the delta t. So I need to take increments of the delta t and add them up. Or in other words, well, before doing the integration, I also have to do the PV. So this one is just the present value to T0. Okay, so I have present value to T0, and my original expression. And now I actually add them up by integration. So the total profit is so equal integral over this expression from T0 to capital T. Okay, now the ERT0 stays from discounting, and if I evaluate this integral, and you would see the workings in the solutions document for the exercises, but I did them such that they support lecture derivations as well. So this integral evaluated right here, it just, once we folded it into derivative, then it's just a question of integration canceling derivative with limits appropriately. So again, a little bit of nearly, very simple integration because it's just canceling over the d. But because of the limits, it's we have vi t minus va t, so vi minus va, and then we have vi 0 minus va 0 because it's the limits are t t0 to t, so larger limit or final limit minus the initial limit. And then after the algebra, we end up with price of the Black-Scholes price of the option at 0, at time 0, minus Black-Scholes price of the option price at implied at, again, at time 0. So simple like this. Now let me show you the result. Okay, so the profit evolution can change, but it always comes up to this story, which is equal VA minus VI.